Vale, perfecto. Y ahora, ¿dónde están los...? ¿No? Eso. ¿Control qué? Vale, control. Vale, Rico, mira a ver si va el...
No se va, eso se va.
No, sí, yo digo si va eso. Ok, now,
Okay. Well, today we are going to prove, to study the stable bursting problem. We say that and we will start in dimension 2, proving the Carnot-Penn theorem. We say that any orientable, complete, stable minimal surfaces in R3 is a plane. Okay? This is a generalization of the bursting problem to this biggest family of surfaces. Okay? Well, as I mentioned yesterday, there are 3 different proofs of this result, and I am going to prove the first one due to the Carnot-Penn. And the proof is like this, it's not complicated. Suppose that phi is the immersion of the surface into the Euclidean space. Then we know remember that we can assume that the surface is simply connected, because if not, we pass through the universal power, which is also stable. Okay? And so I have a surface which is orientable and has a metric. This is, I have a Riemann surface. Okay? Then I can use the uniformization theorem. Then the Riemann surface, which is simply connected, must be conformal to the sphere, to the plane, or to the disk. Okay? But conformal to the sphere is impossible because it's not compact. If it's conformal to the plane, we use proposition, and we prove that must be a plane. Okay? Then the only thing that we have to prove now is that n cannot be conformal to this. Okay? Well, suppose that n is conformal to the disk. This means that the metric of the surface is conformal to the hyperbolic metric of constant curvature -1 in the disk. Okay? But this metric is also conformal to the Euclidean metric in the disk. So our surface can be identified with the disk and a metric here, which is conformal to the Euclidean metric. Okay? But it's important to remark the following. In the disk, the Euclidean metric is not complete, but G is complete on the disk. This is important to remember. Okay? Well, so in this case, the first thing that we are going to prove is this inequality. This inequality is made with the Euclidean metric, everything. And then to prove this inequality, I take any function with compass support in the disk, and I use the stability inequality. The surface is stable. This means that the integral on the disk of the gradient of f squared dv is bigger than or equal to the integral in the disk of the square of f, the length of the second fundamental form. Okay, this is the stability inequality. Now we use that the metric G is conformal to the Euclidean metric. Then in the notes in proposition 1, you have the relationship between both metrics. Okay? Let me write here the curvature of the surface is equal to minus E up to 2u the Laplacian of u. This appears in number 4 in that proposition. Okay. Another property is that the length of the second fundamental form square is equal to minus twice the Gauss curvature, because twice the Gauss curvature is the scalar curvature of the surface. Okay, and also we will use the well-known Dirichlet identity. Okay, so this one is equal to the integral of the Euclidean gradient of f with respect to Euclidean metric. This is the conformal invariant of the Dirichlet integral. It appears in proposition 1 in the note, in number 5. Okay. Then this is bigger than or equal to, and here I use these two formulas to write this one. Then here the integral of the disk of f squared, a squared is equal to minus 2, and k is equal to minus plus e up to 2u Laplacian Euclidean of u dt. Okay, we have used f squared is the same, and a squared is equal to minus 2k, and k I have written in this way. But td is 1 is equal to that 1. This is okay. Okay, sorry, this one here, and then these two cancel, and this is equal to the integral of the disk y f squared the Laplacian of u dt. Okay, so you have this inequality here. Which is just that, okay? This is true for any function, say infinity function with compass form. Well, the second idea is to use this inequality that we have proved in order to get this another inequality. How to do that? Now, here, I change f by f times e up to minus q. This is the idea of the harmonic. Okay? They use as a test function this function involving the function which appear in the metric. Okay? Then I am going to write this one for this new function. Here you have the integral on the disk, and I compute the gradient of this problem. Is e up to minus 2u, the gradient square, plus, here I take the derivative in the second function, plus f squared e up to minus 2u, the gradient of u squared. Okay? And now minus 2f e up to minus u g naught, Euclidean metric, gradient of f, gradient of u. Okay? here appear the gradient of 1 minus f. So this one produced this term, this one is another minus. Okay. Well, now I take divergent here. In order to have a control of this term, I compute the divergent in the Euclidean space of f squared okay. I compute the divergence of this vector field. Then this is equal to, okay, I have not written this one, equal to this term here produce this one because the function is this function. And here appear f squared e up to minus 2u, the Laplacian, the Euclidean Laplacian of u, plus, take the derivative here, 2f g naught, sorry, e up to minus 2u, g naught, gradient of f, gradient of u. Now I take the derivative here, minus twice e f squared, the gradient of u. Okay, so the divergence of this vector field has this three terms. Here appears the Laplacian that now I am going to use here, and these two terms, taking the derivative of these two functions with respect to the gradient of u. Then appear these two. Well, now the inequality that I have here, this inequality, in this inequality I put this thing. Then appear this one. Plus, this term is the same. Minus bigger than or equal to, and I put this information there using the divergent theory. So appear times 4 not and plus 4 okay. Well, this term here from here and appear minus 3. And this one I put here and appear plus 2. Okay. Then this one is bigger than or equal to C. Okay. Now I use the sparring inequality. Consider this one, E up to minus u, the gradient of f, minus f E up to minus the gradient of u square. The length of the vector field is always bigger than or equal to 0. And then this means that 2f E up to u T naught gradient of f gradient of u and or equal to E up to gradient of f square plus f square the gradient of u. Okay, and I put this inequality here, and then this term appear another time, so I get 1. Twice. And this term here appear with 1 time, here appear minus 2. Okay. Okay. Here, this one, I put this inequality, and then appear this term minus 3 plus 1, 2, minus 2, and here appear. I simplify by 2, and I get this inequality. Okay, but now again, this term and this term can be changed by the metric G, and then you get the second inequality. Okay? You can take, using again the invariant of the Dirichlet integral, it's the same with that metric and with another. And then you get this second inequality here. Okay? Then the main idea has been to change to the Euclidean metric in the disk and to use as a test function a function which involves the metric. This is the idea of the carbon. Well, now, from here it's very easy to prove the result. Well, I am going to take a particular function. Of course, I have proved this inequality for the infinity function with compass form, but it can be extended by continuity to the solid space. Okay? Then I consider the typical cutoff function defined on the disk. This function is defined with respect to the metric G. This means that the ball with respect to the metric G. Then for any positive R, I consider the function defined on the disk given by 1 in the ball of center the origin and radius R, equal to 0 outside the ball of center the origin at the radius 2R. And in the middle is equal to the function 2R minus the distance of the origin to P over R. Okay, this is the typical cutoff function. And this cutoff function has belong to the solid space, of course, and its gradient is less than or equal to 1 over R squared, because everybody knows that the gradient of the distance function is bounded by 1. Okay. So I use FR into the second inequality. Okay, and we get the formula. I take in the bone of radius R, I integrate this function E and of course I can put this this number is equal to this one because the function FR is equal to 1 on the bone. Okay, remember that the function FR is equal to 1 on the bone. Now, as this one is a positive function, the integral is less than or equal to the integral on all the disk. Okay? And now I use the second inequality that I have proved. The integral of f squared is less than or equal to the integral on the disk of the function. The function f, the gradient of s e up to minus 2u. But the gradient is bounded by 1 over r squared. Then this is less than or equal to the integral, 1 over r squared, the integral of the disk of this function. But this one is the same that to integrate on the disk with the metric, with the Euclidean metric, okay? But this is the area of the disk in the Euclidean metric over r squared. But the Euclidean, the area of the disk is finite, okay? So if I take r going to infinity, we get that the gradient of u is equal to 0. Okay? Because when I take r going to infinity, the first term converts to the integral on all the disk. And this one converts to 0. Okay? So the only possibility is that the gradient of u. But what does it mean? That u is constant. But if u is constant, we go to this page. If u is constant, g is homothetic to the Euclidean metric. But how is it possible? Because if g naught is not complete, any homothetic is not complete. Okay? This is the proof given by the Carmon-Penny. It's not complicated. Okay? The only thing that they use is the inequality of the stability inequality. And well, the only problem of this proof is that you cannot generalize to higher dimensions because you don't have any uniformizations here. Okay, but in my opinion, it's a nice proof. Well, next week I will prove the case of this theorem when n is equal to 3. And I remember that tomorrow or Friday, the case n equal to 5 will be proved. Well, now, and we are going to prove today another result that itself is important. But I am going to prove that because using it tomorrow, I will prove a very important property of this kind of hypersurfaces, which is that they have only one end. Okay, and this is a quite important property in order to solve the stable version problem. And then the result was given by Schoen and Yao, okay, in 76. And in that result, they related the stability with the system of harmonic function with certain property. Okay? Then they prove that if you take any orientable, complete, stable, minimal hypersurface in the Euclidean space, and you take a harmonic function, which means that the Laplacian vanishes, with finite energy, then automatically U must be constant. Okay? This is the result proven by Schoen and Young in 76. Well, I must to say that this is a corollary of their result, because they prove the result when the ambient manifold is not only the Euclidean space, but also any Riemannian manifold with non-negative Ricci curvature. Okay? They prove the result in a more general context than this one. Well, why this result is important? Because tomorrow we will prove that if some stable minimal hypersurfaces has two ends or more, then having two ends, you can construct a harmonic function with finite energy, which is not constant. So you get contradiction. Okay? Well, so let's go to prove the result. The first thing is to prove that the volume is infinite. Here there are many people studying minimal submanifold and say, okay, you don't need the stability to prove that the volume is infinite. Oh, in fact, tomorrow we will prove that every n has volume infinite. But anyway, I need to prove this property, and this property is very easy to prove when I am assuming stability. So let me explain how to prove this one. Sorry for forget this one now. Okay. Well, I take the same function that here, but in the manifold n. Okay, it means that I take a point in the manifold and I take the ball of radius r and radius 2r around the point P naught. And I define the same function than before. This is a cutoff function which is equal to 1 on the ball of radius r is equal to 0 outside the second ball, and in the middle is given by this, the same one. And then, sorry, forget this one. Here must be a pause. So, well, then I am going to use the inequality, the stability inequality for the function fr. Then I have the integral bigger than or equal to this is the stability inequality. Okay, so I make this is something. I make the same argument that before. I integrate on the disk, sorry, on the ball of radius r. This one. This is equal to, as the function f is equal to 1 on the ball, the integral on the ball of f squared a squared. Okay. Now this function is positive, not negative. So this integral is less than or equal to the integral of the manifold of fr squared a squared. And I use this inequality, integral over m, the gradient of fr squared dv. Okay? But the gradient is bounded by 1 over r squared. And this is less than or equal to 1 over r squared, the volume. Okay? If the volume is finite, if this volume is finite, then this go to 0. Then the hypersurface is totally geodesic. But the totally geodesic hypersurface and hyperplane is have infinite. Okay? Very easy. Okay? It's simply to apply this inequality for this cutoff function. So the first thing is proof, which means that the volume is infinite, and now they prove this another inequality. This is a little bit more complicated because we have to use some property like the Bochner formula, the Kato inequalities, and so on. I will prove later. But before to prove this inequality, I am going to finish the theory. Okay? So suppose that this formula is true, and now I use again the function fr like f. Then I made the same argument, always the same argument. The 1 over m plus n, remember the formula here, okay? F is equal to 1 on the bowl, and then these two integrals are the same because this function is equal to 1 on the bowl. Again, this function is non-negative, then it's bounded by the integral on the whole manifold, okay? And now I use the inequality that I have to prove, and this is less than or equal to this integral here. And now I use that the gradient of this function is bounded by 1 over r squared. Then this is less than or equal to this quantity. But in the theorem, we are assuming that the harmonic function has finite energy. Then what does it mean? This means that this integral is finite, okay? And then if r goes to infinity, this term goes to 0, and this means that the gradient of u is constant, okay? You get that the length of the gradient of u is constant, okay? And now I take the energy, which is finite, this is constant, equal to a real number. Then the energy is equal to lambda square, the volume of the manifold. But the volume is infinite. Then the energy is infinite. This is the conclusion. Okay. So they prove the result. I say using that the manifold has volume, infinite volume, and proving the above inequality. The last argument is standard in this kind of problem. Okay, so I have only to prove the inequality. Okay.
The proof of infinite volume, the second article it shows you like infinite ingenuity.
Que no lo oigo.
The proof when the proof is that the volume is finite. To get the contradiction, the volume was finite, it's an article. But in the intrinsic coordinates, like you can't directly do that because you need infinite injectivity radius, which would then be already defined for the
¿Tú has entendido algo?
Relacionándolo con que si necesita poner alguna hipótesis de radio de divertibilidad.
No. It's a complete manifold. In a complete manifold, when you take a point P and you take the limit of the ball is all the manifold.
The ones are extensive. Ones are extensive.
¿Son intrínsecas o intrínsecas?
Intrinsic. All the balls are intrinsic. Okay. In a complete manifold, you take the point P, any point can be connected with the point P by a minimal geodesic. No problem. Intrinsic. Well. Well, to prove this inequality, I have a harmonic function. In some sense, I have to use test function which involve the function. Okay? So they define this and they take the following. They take any infinity function with compass support on the manifold. And now they use this function, the length of the gradient of u. But this function is very obvious. It has zeros, and in the zero is not infinity, and Then I'm going to take an approximation, a smooth approximation of this function. Okay, for any delta positive, I define A delta is equal to the square root plus. Okay, this is infinity, manifold, and when delta go to 0, A delta go to 0. And then we have work we need without any problem. Well, they use as test function this one, F A delta. Okay, and they put F A delta in the stability inequality. Well, let me compute to make some computation here. The first one that I am going to use is that A delta square is bigger than or equal to the gradient of U square. Okay, simply come from here. And the second one, the gradient of A delta is equal to 2A delta in the and the gradient of okay. Well, then I use the stability inequality, and I have that the gradient of F A delta square is bigger than or equal to the integral of F square A delta square, the length of the second fundamental. Okay. This is the stability inequality, and then we are going to make some computation and to use another result. The first one is here, the gradient of F A delta gradient of F plus F gradient of A delta. So this inequality becomes A delta square gradient of F plus F gradient of A delta square plus 2F A delta G gradient of F gradient of A delta. This one, this is bigger than or equal to the integral over N of F square A delta square, the length of the second fundamental form. Okay. Well, here, if I put the gradient of A delta like this, and here again, we change this inequality by this one. The first term is the same. Here appear this one, the length of this vector field to the square, or A delta square, and the gradient of this one square. Okay, I am putting this one here, this one here. And here, 2 and 2 disappear, and A delta disappear, and then appear plus F G gradient of F gradient of W. Okay, putting here the gradient substituting by this one, and then disappear. This is bigger than or equal to 1. So we get this inequality. And now I am going to use some result related with the harmonic function defined on a manifold. Probably better to consider the divergence before. No. Yes, I'm going to compute the divergence f squared gradient this one. I compute the divergence of this vector field in order to have certain control there. Okay? It's exactly the function. Yes. Then it's equal to f squared Laplacian of gradient plus 2f g gradient of f gradient this function. It's seen that I am complicating the formula because I am introducing the Laplace, but I am going to use the Bochner formula or Weissenburg formula as you like, because we can have a very nice control of this. Okay, so it's very convenient to put there. I am going to try. Now we use in the notes lemma law in section 4. Okay. Then the first one that I use is that 1/2 the Laplacian of the gradient of a harmonic function, this is the Bochner formula, is equal to the Ricci curvature over the gradient plus the length of the Hessian square. This one is the Hessian of the function. Okay, this is the classical Bochner form. But I am in a hypersurface. So the Ricci curvature is equal to minus the second fundamental form over the gradient of u squared plus the length of the Hessian. Okay. Now I use in this lemma the third property, which is like a Cato inequality. And the third property is say that A over the gradient, the second fundamental form over the gradient, is less than or equal to n minus 1 over n, the length of the second fundamental form times. This is like a Cato inequality, and the proof is in there. Okay? And also, finally, I use the Cato inequality, in which he bound the length of the Hessian, which is the part 2 of this result. We say that the gradient of u squared times the Hessian of u squared is bigger than or equal to n over 4n minus 1 equal. The classical Cato inequality. Okay. In order to get this inequality, and this inequality is quite important to think here that the trace of A is 0. And here with the gradient, that the gradient that the Hessian is symmetric and another important problem. So from these three equations, I can put here, remember, that this vector field is always less than or equal to A delta squared. Okay? So I can put here A delta squared, the Hessian Right? Then I use this inequality and this inequality, and we put bigger than or equal to, or A is smaller, the opposite is bigger, minus n minus 1 over n, the gradient of u squared, a squared. And here, this one is, this function is positive, I put it in here, plus n over 4n minus 1 a delta squared. Here, the gradient of this one. Okay? So I have this inequality. And I'm going to put this inequality in here and to use the divergence. Okay? So first, here, I am going to it's important to remember what to do before. Yes. Well, here I use the liberty. Okay. Then I obtain the second term is the same. Here appear FG and there appear 2. Then I put minus 1 half f squared Laplacian. Okay. Okay. Is bigger than or equal to f squared a delta squared a squared. This is the last one. Now I use the inequality that I have obtained. That inequality in green. The Laplacian is bigger than or equal to, the opposite is less than or equal to. Okay? So this term is the same. It's the same. This one is equal to minus this one is less than or equal to that one with the opposite sign, okay? I don't know if I need some coefficient here.
That's where it is.
Yeah, it's very difficult from here to see everything. Okay?
You need an F square in the third term.
Okay, F squared. The coefficients, okay?
Yes.
Well, okay. I have put this three term bigger than or equal to this interval. Okay. Now, these two terms are equal and appear here 1 and here minus n over n minus 1. This is 1 over n minus 1. Okay. This one and this one. No?
Yeah, you have another n minus 1 in the denominator.
N over.
Ah, no,
This one is not necessary. It's a mistake. Then n minus 1 is 1 over n minus 1. Okay? So I can put here, let me read 1 over n minus 1. No, not here. Sorry. Oh my God. Here.
That was
And I don't remember what.
n minus 1 over n.
Thank you. And this is here, okay? And now, let me see the inequality that I am looking, grading. This one is okay. This is no problem. Now, I put this one in the second term, minus n minus 1 over n, the gradient, a square, okay? And how is this term? Not negative. It's bigger than the roots. Okay? I put bigger than 0 here. Okay? So finally, you get this inequality. The integral of a delta square, the gradient bigger than or equal to 1 over 4 a delta n minus 1 f squared gradient. Okay. ¿Cómo?
En esta parte hay un más.
En esta parte hay más.
Ahí, justo enfrente, el signo es un positivo.
No debe.
Pasa al otro lado, tiene que ser negativo.
No debe.
Todo un menos, ya está.
No debe. No, esas cosas no. No sé.
Sí, de broma.
But because it was minus 1 over n minus 1. That's
This one?
yes. The last on the bottom.
The green. Yeah. There,
Look at the sum.
And
One
I,
minus. Yes, that one is minus.
Minus.
you see, put a minus.
Very much for following you. So this is okay. Okay? This is okay. Now we use again this one, the gradient, and you have this 1 over 4. This is a delta square. Okay? this is equal to the integral of f squared over n minus 1. Here appears the gradient of nabla, a delta. Okay, the gradient of a delta square into all this. Then you have this inequality, and now you take delta going to 0 and finish. It's not complicated result. When you read the original paper of them, in which the ambient manifold is a manifold with reach non-negative, the thing is a little bit more complicated, but it's the same. Okay. Okay.
So, thank you for this presentation.
Okay.
La parte final yo ya no sabía si...
Because a delta converts to the gradient.
Ah, okay, it was the square root. Okay, okay, okay. Okay, the root.
A delta converts to the gradient, not the. Okay.